Okay, people, welcome to my talk. My name is Jack Summers, and I am I run this 501c3 Smoky Mountain Scientific. Today I'm going to tell you about work that we've done for our spectrometry project. Let's see, we are a 501c3. Our mission is to develop and manufacture and market open source instruments for science education. And we have a number of instruments. Today I'm talking about the spectrometer. Let's see here, how does that work? Oh, there we go. All right, so first thing to talk about is optical elements, right? So up on in the center of the screen here, we have that's a concave mirror that is used to focus light. Down here, this is an optical slit that lets light into our spectrometer. This is a collimating mirror and a diffraction grating. All right, so these are the four optical elements that are required to make a spectrometer, at least the ones that we are working with. And these things are kind of expensive if you go out and try to source them from commercial sources. So what we do is we have these manufactured and in a reasonable amount, and that means that we can sell them for a relatively low price point. And we'll be selling those out of our website, Smoky Mountain, smokymtsci.com, and I'll have that later in the presentation. Okay, so we need to have an optical bench, right? So we're using the crossed Zerny-Turner geometry, which has the slit at the bottom of this figure, and white light comes into the collimating mirror, which is mirror 1. It reflects into the grating, which is over here. The light coming off of the grating is diffracted onto the second mirror, which is the focusing mirror, and the focusing mirror focuses the light onto the detector, which is a charge-coupled device, a CCD. All right, so there are a number of design challenges associated with making a spectrometer. You need to have a precisely defined optical geometry, right? So how do you calculate the locations and the positions, and the orientations of the optical elements? And then how do you translate that design into making a physical object? Okay. The answer to these questions, we're trying to make something that's 3D printable, right? So this slide shows an old design that we had, and we designed this in SketchUp. A lot of people have 3D printers, so we believe this is a good method for making low-cost materials. We're unhappy with the SketchUp freeware because they keep removing functionality from it, and we've changed to working with something called OpenSCAD. So OpenSCAD is a free open source computer drafting program that interfaces well with 3D printing. Okay, there are three panes in this window. There's an editor over here where you write computer code, and there's a console that allows you to output numbers and information, and there is this viewer that shows you a rendering of your design. So since this is a computer program, it allows you to do precise calculation and use that to place your elements and figure out where your light's going. Okay, so as I said, you should be able to change the adjustable parameters. Over here, this shows a little piece of the text editor where you're putting information in, and you can choose the focal length of your mirror over here. You can choose any number that you want. You can put in there. You can put different wavelengths, and the short wavelength here will end up being this blue blue stuff that will focus onto a point. The long wavelength will give you this red ray tracing, and the one in between will give you this green ray tracing. You're allowed to put in different number of lines per millimeter of your grading. This is set up for 600. You can pick a lot of different distances and angles to put into your calculation, and this OpenSCAD will generate some position and orientation parameters that you can then put into another program, which will output a three-dimensional figure, and then you can turn that into an STL file, a stereolithography file, which can be 3D printed. And if you don't have a 3D printer, you can most likely use one, access one through your local library or your university, or you can just go out and buy one. Anyway, once we made the STL file from this, we put it on our 3D printer and printed this physical spectrometer. Okay, as you can see, there are a number of black parts which are housings. This black piece in the front has the optical slit behind it. This is a fiber optic connector. There's a small ball lens behind that fiber optic connector, and then over here we have that's where the collimating mirror is. There's a mount behind the collimating mirror that holds it in place. Here are two mounts that hold the diffraction grating in place. Here is the mount for the focusing mirror, and then over here this is the CCD and attendant electronics. All right, so the electronics are based on this Toshiba CCD, and you have the spectral response. You can see this goes down below 400 and up to about 1,000 nanometers, which is where that detector is useful. You can change the orientation of the diffraction grating by printing different angles for the mounts, right? So this shows you a figure of a mount that has an angle set into this, and that will allow you to change the wavelength region where the light focuses, in case you don't have your spectrometer exactly tuned the way you want it. So there is some adjustability. So this spectrometer body over here we calculated for giving us the centered between 300 and 700 nanometers, and this is the spectrum that we acquired. This is the spectrum of a, what's it called, a compact fluorescent lamp, which has known wavelengths of emission. I believe this one over here is 611 nanometers, so we can do a calibration, and you can see that 300 to 700 is not exactly centered, but it's not too bad. All right, so we have some stray light giving us variation in the background when we use this translucent orange plastic, right? So what I'm talking about here is this background noise. It's not noise, what is it? It's stray light that gets into the spectrometer. I took this spectrometer, and after acquiring these spectra, I put it in a cardboard box and acquired 18 more spectra, and you can see that they align very well. So the idea here is you don't use the translucent plastic. All right, so we also came up with electronic hardware. All right, so we have this CCD detector. We're using the Teensy 4.0 microcontroller board, and we had fabricated a board that connects the two, and also has an amplifier, a series of amplifiers, and a 16-bit A to D converter. All right, so this shows you another view of it. That's the top view. This shows that the CCD, the detector, is on the bottom side of the board. So this part goes inside the spectrometer. This other part sits outside the spectrometer, and it seems to work pretty well. There's a lot of embedded electronics that we have to deal with. We're collecting data at 1 megahertz, so we need to calculate, we need to get our 16 bits of data off of our ADC in under a microsecond. And this slide shows a scope trace of that. All right, let's see here. We have a couple of different interfaces that we're working on. One of them, this one I'm showing you here, this is dedicated to calibrating our spectrometers, right? So we have two directions we need to calibrate in. We have the intensity direction and we have the wavelength direction. And this interface is set up to allow you to calibrate the wavelengths based on the wavelengths, the emissions of a compact fluorescent lamp. Okay, so this peak here is observed at 404.6 nanometers. This one's at 435.8, and etc. We come down. We pick. We have a way of peak picking. You just drag this little box, and it'll take this. These crosshairs to where you're trying to get it to. You select the wavelength that you want to assign, and when you hit the select wavelength button, it will tell you which pixel on the spectrum you're looking at. Once you have the pixels defined, you hit the refine, and it will do a least squares refinement to give you a baseline a wavelength calibration data that you can store in that will be stored in non-volatile memory. You hit the right cal button, and it stores that information on the spectrometer, on the microcontroller of the spectrometer. So that is how this calibration, the wavelength calibration, is done. You can calibrate the vertical dimension, the intensity dimension, with this low reference and high reference. These are values that get transferred to the microcontroller. They are output into PWM signals, which are voltages that are used by, first of all, the amplifiers to give you an offset. The low reference will give you, will change this dimension, the height of the baseline. The high ref will change the intensity, the high intensity level. Okay, and I have videos. I have YouTube videos available for looking at this information. All this information should be available from our website, SmokyMountainScientific.com, SmokyMTSCI.com. Phew. Okay, so this shows some old data of absorbance spectra, and I don't really feel like getting into this. This is this is the lamp that I acquired that information on. It's got a fiber optic connector. It's got this compact fluorescent lamp. This wooden box fits over this. It's got a little switch over here, and that's how life is. I think I'm about done with what I want to tell you. We got a whole bunch of stuff that we did, and yeah, and if you have questions, I'll be happy to address those. All right, so thanks a lot for listening.